there are various kind of conceptions around what the automation actually mean. Everything from kind of autopilot and full autonomous, on a plane or, in a Tesla, to more kind of simple advisory and analytics services via web apps, etc. But irrespective of where you kind of fall in the spectrum, there's a couple of developments around why automation is very contextual right now, especially when it comes to artificial intelligence. Some of the materials I'm referencing here in the next slide, it's actually from very good work done by the Drilling Systems Automation Technical Session. It's called DSATS. It's a subcommittee of SPE. Some of you may be very familiar with it, but they kind of provide a framework and roadmap for where automation is heading. So as everyone knows, wells are getting more complex. Drilling windows are getting smaller and smaller in unconventional U.S. land. Let's say they're 20, 25 feet now. There's a lot of data coming off these rigs. An EDR system might have 40 to 200 channels, and then when you look at the control systems, that could be 4,000 measurements every second. And then the consequences of costs in terms of NPT and risks, those are heightened. And then, of course, there's a lot of, I guess, thought going into today's environment where there's a lot of reorganizations. So transfers from, let's say, skilled employees and various kind of employees with different types of training, that kind of continuity is important. And AI is a mechanism to do that. This slide, it's not meant for you to, be able to see everything. The text is quite rich, but it's a summation by the DSATS group around the various models that are relevant to drilling automation and optimization. And so these models, the first two actually have to do with rate of penetration, but there's also relevancies and models around hole cleaning, predictive pressure management, anti-collision survey, mechanical earth models, pore pressure models, etc. There's a lot of different models. What Quantico focuses on is how do I optimize your ROP? And so in these first two rows here, where it's really about ROP optimization and in real time and pre-drill, you'll notice that there's various inputs as this table lays out. And I think as, perhaps intuitive, some of the key drivers for ROP optimization is, of course, your rig state and the condition of your equipment, but it's also quite driven by some of these attributes like resistivity, porosity, gamma, compressive strength. In other words, it's the full closed loop modeling between the feedback and response systems in the rig and drill string and BHA, coupled with the dynamic earth properties. All that taken together is that full closed loop automation that Quantico is pursuing. And there's various automation companies out there. We tend to kind of, I guess, attract ourselves to the ones that are more interested in that holistic closed loop optimization. And of course, the last thing I want to mention on this slide is as these models run, there's only a few parameters that the drillers can influence. So weight on bit, the rotation, and the flow rates. You can adjust them higher or lower. They're on the order of magnitudes of seconds to minutes or every stand, however you like. And then there's consequences, right? If you have excessive ROP, you have damaged bit. If you have excessive pump pressure, you might damage equipment. And so these are well-known physics-based models. And the question in today's webinar is, how does AI enhance and automate and speed all this delivery? So at Quantico, again, there's various approaches, but we take a particular approach of, the rock property variability, that is a missing parameter in most historical models, and certainly from real-time models. The real-time implementations often, the few that are run, use LWD sonic tools. Those are 100 feet or plus behind the bit, so not really relevant to the exercise in our view. So the approach we take is we have a service called QEarth, and we're not going to go into these services very much. I'm going to skim them at a very high level. But it's basically using a combination of seismic and offsets and LWD logs, providing the rock properties ahead of the drill bit, through the entire seismic volume, which can translate into thousands of feet ahead of the drill bit, either laterally or vertically or deviated. And then once the drill bit hits that rock, there's a gamma sub. And once you reach the gamma sub, you can take the gamma LWD log, add the drilling dynamics like your torque, weight on bit, RPM, etc. And we have a patented service that's around how to use that suite of information to generate high accuracy synthetic sonic and density logs. The advantage of this is it takes into account the new data that you have when you hit that rock, which is your gamma and your drilling data, which is much closer to the bit than a sonic LWD tool. And then at surface or in the cloud, how do you optimize all these parameters with rock strength, with offset data, with mechanical specific energy? So the QDrill part is the optimization algorithm or engine for QDrill. As I mentioned before, other webinars have covered QEarth, which is the AI-based Earth modeling service. Once an Earth model is fairly automated, before drilling, you kind of set up the architectural parameters of the neural networks, etc. The advantage of that is as new LWD, gamma, or other data, QLog data comes in, you can automate the update of the entire Earth model within minutes. And so as you see in these series of visuals, this is in the Permian and Midland County, but as more logs come in, you are getting an updated view of the Wolfcamp, which is kind of this middle section. And if this can happen in real time, that means that you are able to see ahead of the bit, either vertically or in lateral, space, which could be very interesting. The other two aspects of QEarth that are very cogent to this conversation is the resolution is typically in the unconventionals with good quality seismic. It can be as low, as high resolution as 10 to 15 feet resolution versus traditional seismic resolution of closer to 40 to 60 feet. And so when you're talking about drilling windows that are 25 feet, the importance of the resolution is obvious. And then secondly, traditionally seismic workflows are very challenged at providing some attributes like compressive strength that are very relevant to drilling. And because this is machine learning, we can map compressive strength, stress, brittleness properties as easily as acoustic impedance or other kind of geophysical type parameters. There's some papers on QLog. I'm not going to go into it in depth. It's been covered in other webinars, but the essence is basically training on offset wells. You take the LWD, gamma, and drilling data. You feed them into pre-trained models in the U.S. land. Quantico has hundreds of horizontal measured logs from which we've built multi-client models. And so when you're drilling in a deviated space, outputting sonics and densities real time at the gamma tool, it gives you much more relevant and timely information and takes advantage of all the data coming in through the system. This is just a case study on QLog. It's an SPE paper published at the SPE ATCE last October. It's some work with Shell where, there's comparisons of various AI tools and looking at the drilling response data like ROP and how do you get effective synthetic logs, through the QLog method. And so just a reference that if you're curious about QLog, there's a paper that can be distributed. Okay, so that's kind of the background. That hopefully paints a picture of how do we provide specifically compressive strength, but other kind of rock properties ahead of the bit. And then once your bit hits that rock, the near bit properties around that. Now the question is, how do you use that for AI-based drilling optimization and automation? So I'm going to start with an example. So at a very kind of fundamental level, providing compressive strength real time behind any drill bit without using expensive, jewelry, that I think has value, and UCS logs can be interpreted by drilling engineers to assess all kinds of drilling dysfunction issues. This is a case study from Wyoming. This operator had, in this case, 6 wells in an area, and you can see it's been laid out by different sections, right? And what the numbers represent is how many bits were used in each of these sections. The cost of a trip, as folks on this call probably know better than me, at this point in time is about $130,000 for a trip. So minimizing unnecessary trips was very important. But you can see across these wells, it was highly variable how many bits and trips they had to make. Even in certain sections, you had variability from 1 bit to 3 bits, 1 bit to 4 bits, 1 to 5. And so not only was this very expensive for this operator, it's how do you mitigate this? How do you standardize and mitigate? There was a lot of analysis done where we looked at bit dull reports. So we kind of identified, what instances where you had DVR, where you had broken bits, you looked at photos, etc. And that kind of validated that there was really no rhyme or reason, based on the simple data that was available on why there was such variable drilling performance. Now we bring to bear the AI and the pre-trained models, where what this shows is an indicator of the compressive strength volatility or gradient, from surface to kickoff to the lateral and through the lateral. What this means is in green, it was fairly stable compressive strength. But when you get to the oranges and red, it was very, very volatile into kind of extreme standard deviations of volatility. So what this kind of showed was a couple of interesting insights. One, across these 3 wells that are very close to each other, there's actually very little correspondence. If you used well A as an offset and projected that UCS pattern into well B, it really wouldn't help you very much. You can also see that there's quite a lot of volatility naturally in the vertical section compared to the deviated and the horizontal section. Not only did that cause excessive bit wear, because the drillers who are, don't know that this is going on, they're just trying to kind of, hit their set points. They're kind of drilling through these hard stringers, and the transitions from hard rock to soft rock and vice versa were damaging the bit. The equivalent effect of driving a car through a brick wall. The car is going to make it, but it's not going to work on the other side of the well. Other kind of issues that you saw was a lot of tortuosity, micro dog legs. Half the time was probably spent trying to get back on path. So not only do you have the cost of excessive tripping, but you also have the arduosity. and tortuosity. And so the point here is that with AI, you can take the drilling data and gamma, generate compressive strength logs real time, look back on hundreds of wells, and really kind of examine what are the types of drilling dysfunction going on. And that examination is really via a human interpretation of data that would not be available without kind of an AI approach of getting the compressive strength. Now we're gonna transition to maybe a more complex type of drilling optimization. I think there's various people on this call right now that are probably more subject matter experts than Quantico, but it's a fairly standard and well-known state of the industry around using mechanical specific energy for drilling optimization. There are schools of thought around how do you design and optimize limiters and reduce limits along the way to get optimal performance. There are papers around how do you look at compressive strength, ROP optimization. There's a well-known kind of body of work in these areas. What we tend to focus on is Quantico is combining compressive strength with mechanical specific energy. And again, the compressive strength is via the artificial intelligence. When you look at mechanical specific energy, there's a well-known equation of how to calculate that, and the challenge of MSE is little in this formula that actually reflects the rock mechanics downhole. Indirectly, one could argue the ROP is an indirect response mechanism to changes in rock. But I would say with all the other things going on in the drill string, I would not say ROP is a one-for-one proxy for rock strength. And so the issue is inefficient drilling. There's the energy that is required to break rock. That's a compressive strength. This is represented by this light blue line. And then there's energy applied into the rig and drill string and the motors, and that's the mechanical specific energy. Ideally, in efficient drilling, what you're looking to do is just apply a little bit more energy than required to break rock. When that delta is significant, as we see here, that is a very strong sign of drilling dysfunction. And knowing when the MSE is changing because of dysfunction versus just a natural change in the strength of the rock, that is what allows the automation and the AI to determine and optimize the drilling parameters effectively. How important? I think that there's this notion out there that, well, if you're in the lateral, you drill through it very quickly. Well, how big a deal is this, right? So this is a lateral from the Permian, mapping compressive strength. You can see here there are changes on this on each of these kind of grid marks. It's 5,000 psi. So if your psi in terms of MSE is 20,000 psi, 30,000 psi, these 5,000 or 10,000 swings in compressive strength can be quite important to the full picture. And again, in a lateral, you cannot project from an offset lateral. The lateral geologies changes, quite unpredictably, and then you have well tortuosity to other things that are affecting, these compressive strength values. Now, if we kind of look at the fundamentals of MSE and UCS, this is a little bit of a deep dive into the physics of this, but you have a sources and uses of energy. The sources of energy is represented by this left column. You have the surface measured energy, which is basically your MSE. You have things around the motor efficiency and the motor inputs, which relatively, is a smaller amount of the energy. And then you have the uses of energy. This large bar here is the energy to carry and rotate the drill string. Then you have bit efficiency and to rotate the bit, and then you have the energy needed to destruct rock. Now you can plot these things where there's on this graph to the right, there's compressive strength in this red and purple color, and then there's mechanical specific energy in this blue and green color. And you would naturally, as you drill, expect MSE to increase because there's a natural the torque and drag from more and more drill string. But you see that the MSE here is quite volatile and often deviates from the naturally expected energy loss. But you can map this, and the difficulty in mapping this historically is, well, people could derive the MSE, but there's really no picture of how the rock was changing. It's a little bit like driving a car on a road, and you're trying to steer the car or set the gas just based on the feel through the steering wheel and the suspension system. And there's no window or windshield to look through to see how the road is actually changing. Imagine how difficult that is. So using the same data, this is an example of a real situation where this was a Permian well. This is in the lateral section. There was a bit trip made at about 16,000 feet, right? What the operator was seeing here was that the MSE was climbing and the ROP was decreasing. And I think that the concern was there was a lot of drilling that had already happened, and maybe the bit was getting prematurely worn. It's a very difficult decision on what to do because they're so close to TD here that do they pull out and call it TD? Do they pull out, replace a bit, go back in and finish the lateral? Or do they just leave the bit and try to drill through the rest of the design lateral? In this case, they tripped out. What they did not have is a benefit of the compressive strength log. And what you see here is that actually the rock was getting harder here. And so if you had the advantage of this log, you could have inferred that whether there was a dull bit or not, perhaps drill through this hard rock section at slower rate and then build rate back up through the rest of the lateral, or make the determination whether after this the rock kind of settled down, whether ROP was still slow. So this is a case in point where the bit got pulled, $130,000 plus or minus. They looked at the bit, and the bit was actually fine. It was an unnecessary trip that could have been averted had they seen some of this information, right? So this is a little bit, kind of the automation that can work. Now, how do we actually implement the AI automation? I think it's pretty well known that there are companies and there's contractors out there too, but you can contact them and say, for each section, tell me what you or other operators see as a range of drilling parameters. And operators have kind of their standard operating procedures of well-known set points for each section. The issues with that is none of those give you the local optima of what should weight on bit, RPM, and flow settings be as the rock changes. And so the power here is twofold. One is the AI, through all the logs and drilling data in the region, can generate these compressive strength logs. The AI can give you a view of compressive strength via the seismic before you even hit that rock in very high fidelity. And you can compare it to MSE. And so if one were to say, look at all the offsets, where did I see similar patterns in compressive strength and MSE behavior? In those patterns, which of those instances led to good ROP? And then tell me what those drilling parameters were that led to good ROP and project them into the next foot of rock that I'm drilling. What this visual represents is basically taking offset wells and taking properties like UCS and MSE and you know, EDR data, et cetera. You normalize them across all the wells, you vectorize them, and you do pattern matching. The higher the value on this y-axis, the more distant that pattern match is. So what you're looking for is a good pattern match where you know, it's close on various dimensions of a multi-dimensional Hilbert space, and that is what allows you to project parameters from one well to another that you're drilling, but with the contextuality of both MSE and UCS in a very automated fashion. And the Qdrill service itself is an advisory service, right? Because all this data can be taken in from the EDR, Pason, Totco type systems, and it can output back for you, you know, increase weight, decrease weight. There's, you know, gauges that can reflect what the advisory should be. There's various case studies been done where we've looked at laterals in the Permian, and we found that, you know, one, our analysis corroborated with what the customer saw in terms of vibration and ROP issues. And two, we were seeing in the laterals, in this case, 3 wells, about 30% of the lateral was drilled inefficiently. So when it comes to the cost per well, but also what's the variance from well to well, if you can tighten that standard deviation of well delivery and drilling days, that all, you know, saves money for the oil company. And then, you know, the big picture is level 1 kind of optimization / automation is really just advisory, where you take in from the EDR systems and provide advisory. There is work that Quantico is in pursuing with third parties where you have level 2 automation. That takes into account the rig systems and the control systems. Why this is important is then you can get sub-second type communications. And 2, the control systems, again, I said earlier, has about 4,000 channels a minute, in a second in some cases. So you get all these subsystems that provide much more feedback to also revise and enhance and continue to search and seek out that local optimization function for those parameters. In summary, is a comparison of a traditional, you know, rules-based approach where you look at offset wells. The AI approach, it provides real-time data for the well you're drilling. It accounts for lateral variability and provides for measurements of the rock ahead and close to the bit. Traditionally, work has been done on MSE monitoring. Now the power is, what if I couple a closed loop system with real-time compressive strength? Traditionally, it was set points standardized in advance by section, you know, before drilling. Now you have full data mining in real time of offset wells for the, you know, specific variability in the well you're drilling and in that, you know, next section of rock. And traditionally, it's been a lot of experience and subjective interpretation. And now this is really about not taking away that human experience, but how do you augment that to deliver faster response times, lower cost, lower standard deviation, and provide more consistency in performance. And that is my presentation.